Thank you, Bridget. And I would like to thank the organizers for the invitation, and also like to thank for their incredible effort to make this virtual conference so much fun. I had a lot of fun. So I'm going to talk about free thiols regulate the interactions of self-assembly of thiol-passivated gold nanoparticles, investigate with X-ray scattering and MD simulation. I'd like to acknowledge people involved in this work before I run out of time. It's done by a group of us at Chemicars, Pansun, our postdoc, Weibu and Marino Barrow, our beamline scientist, and a group of undergraduate students that I supervised at the University of Chicago with Professor Stuart Rice and Professor Mark Schlossman from University of Illinois, Chicago. The system we study is a 2D self-assembly of gold nanoparticles at the air-water interface. The Xiaoming Ling and from Argonne National Lab and Josh Portner from University of Chicago synthesize the particles for us. And they have a core, these particles are core about 5.2 nanometers, and they have a quite narrow size distribution. They're passivated by dodecan thiols, and we suspended them in the toluene. When you spread them on the surface of water, the gold nanoparticles just form monolayers. And these nanometer thin films exhibit quite interesting elastic properties. And we observed that when you compress at the air-water interface laterally, these monolayers will buckle into bilayers and trilayers, and then it will wrinkle and unfold like a piece of elastic film. Jaeger's group from University of Chicago measured the freestanding monolayers, gold monolayers, Young's modulus. They drip this monolayers onto a TM grid and poked with AFM tips. And when they found that the Young's modulus is on the gigapascal order of magnitude, which is stronger than nylon and most polymer films. In fact, this film is so strong, they can sustain the pressure of aqueous solution filtration. So over the years, we are interested in tuning the elastic property of those monolayers at the air-water interface. And we found that many factors affect the elastic response of those monolayers. For example, the dodecan thiol, the composition of the ligands, the different type of cores of the nanoparticles, and the polydispersities, and it all contribute to the property of elastic response. And we can also enhance this elastic property by cross-linking the ligands in situ at the air-water interface, thereby changing this strong but rather brittle films into a more fabric-like films. However, the most effective way of changing the elastic response is to change the ligand concentration in the nanoparticle suspensions. So the mechanism for the two knobs mentioned above here is quite straightforward. However, the last one is not. So we have been asking ourselves, why would the ligand concentration affect the elastic response of those gold nanoparticle films? And the second question is, where are the free thiols distributed in the gold nanoparticle monolayers at the air-water interface? So those two questions serve as an outline for the rest of my talk. We determined the ligand concentration by measuring the mass of the ligands and the gold nanoparticles with mass spectrometry. we determined with a solution of lowest thiol concentration to determine the ligand mass fraction. And then we'll add ligands back to those solution with low concentration to form different ligand concentration of the films. We observed that the monolayers of a different ligand mass fraction give us a different elastic response in terms of wrinkle and fold. And when it reached the concentration above 30%, around 30%, this wrinkle fold behaviors kind of disappeared. And so meaning the films are much more viscoelastic. And we also measured the Young's modulus of those freestanding film as a function of the ligand mass fractions. We found that it peaked around 20%, which is giving us the best wrinkle and fold properties. And then it dropped quite rapidly after the 30%. And we'll come back to this 30% later. So why would the ligand concentration affect the elastic response of the gold nanoparticle films? Or simply put, where have all the thiols gone? And there are basically two hypotheses in the field. The first one is the gold thiol bond is a covalent bond. So the thiols will not fall off after they're bonded to the cores. So in this picture, the nanoparticles are always fully ligated, regardless of the thiol concentration. And then removing the free thiols will not remove the thiols from the gold nanoparticle core. However, this hypothesis cannot explain why the gold cores become sintered and form dimers and trimers, because if they are fully ligated, they just can't touch each other. So the second hypothesis is that the gold thiol bond is not that strong. In fact, they're weak enough that the Langmuir kinetics is applicable to the kinetics of the thiol absorption. In other words, there is equilibrium between the free thiols and the bonded thiols. So in this picture, the free thiols are always present in the solution. And it is this free thiol concentration that regulates the coverage of the bond thiols on the gold core. So the Langmuir absorption kinetics provide a quantitative relation between the thiol coverage on the gold, what we refer to as a core ligand coverage, and the free thiol concentration, C1, which is also related to the fractional bonded thiols concentration. We note here that this free thiols and the bond thiols concentration together give us this ligand mass fraction percentage. So here we show the quantitative relation between theta and the ligand fraction. And you can see that below 30% of ligand mass fraction, the thiol coverage increased rapidly. And after that, it increased very slowly. So this hypothesis agrees with the TM observations, because at the low thiol concentration, the gold particles are losing hairs and they become bald. So the cores can't touch one another. So now we know that there are always free thiols in the solution. And we ask, where are the free thiols distributed in the gold nanoparticles at the air-water interface? Specifically, we ask, how do free thiols affect the structure of the gold ligand shells and their environment? And also, how do the free thiols affect the location of the gold nanoparticles with respect to the surface of water? So we address these questions with MD simulations and X-ray scatterings. First, we'll look at the MD simulation results. which was carried out by a then very talented undergraduate student, Lindsay Novak, who was now a graduate student at MIT. Her system consisted of a single gold nanoparticles of different ligand coverage and equilibrium either with free thiols at the surface of water or with just bare air-water interface. And here I'm going to show the result with thiols at the interface. So at the lower thiol concentration of a 22% coverage, which experimentally unachievable, the thiol distribution around the core is asymmetric. There are more hairs on the top than at the bottom. However, when theta increased to above 65%, the thiol distribution becomes symmetric. It's asymmetric, disappeared. In addition, she found that the nanoparticles actually make a dimple at the air-water interface. Her result also shows an interesting behavior of this free thiol layer at the interface with and without the gold nanoparticles. Without the gold nanoparticles, the free thiols behave just like surfactant, forming a monolayer at the interface with the sulfur atoms anchored at the interface. However, when you place these gold nanoparticles on top of the film, you see the sulfur atoms become disordered and randomly distributed along the film, meaning this film will become more bulk-like liquid. And as you increase the coverage, the film become more disordered. So this indicates that there is a strong interaction between the free thiols and the bonded thiols. So now we talk about X-ray scattering result. The liquid interface X-ray scattering experiments are done at our beamline at Chemical Cars Sector 15 in APS. The lead beamline scientist is Dr. Wei Bu here. At the end of my talk, I will briefly describe our instrument and the upgrade. So now continue. We measure the X-ray reflectivity and GID of the gold nanoparticle films of different concentration. Pan Sun, our postdoc, was leading the experiments and data analysis. So here we show a typical Bragg rod diffraction pattern for this gold nanoparticles. So it shows that these nanoparticles self-assembled onto 2D crystallines at the air-water interface with a hexagonal packing. And we can determine the center-to-center distance of the nanoparticles. However, we're more interested in the edge-to-edge distance to be compared with this all-trend ligand dodecane thiols. So we can see in this plot that this edge-to-edge distance increase slowly when the surface coverage is below 95, and then increase rapidly above. I want to note that it's very high concentration, large separation between particles is smaller than the two stretched dodecane thiols, meaning they're quite to digitate is happening, which make the particle strong. And now I'll talk about for the X-ray reflectivity. Quite complicated model. We do the forward ice distribution, and then we allow the free thiols fill between the nanoparticles, and we allow particles at the interface and introduce the height parameter between the core to the surface of water. And we introduce like instead of a shell here. And finally, we model this free as a thin film with a variable thickness. Point out that this is not the only model that we use for fitting. In fact, we using on and way and try to find other models. And the other I described to give us the chi-square value. So X-ray reflectivity fitting and the electron density profile free films, the thiofilms. And as the concentration of increases, the from the water surface and the thickness of the thiofilms. This height parameter is getting reflectivity fitting that below the about 5% coverage core of directly on the water. You reach to this about 90%, the nanoparticle moving from water.
Binhua, I can't hear you anymore.
It's
already like 5 minutes, kind of crazy, kind of like.
So the
you're kind of breaking up, yeah.
I don't know where to, I should know the video. Okay. That's here. It shows from the MD simulation out, and that does not show this critical value behavior. I believe because we model core as a sphere for polyhedral gold with flat facet as in the experiment. So both the GID, the reflectivity, there's a critical value of 90%, the core ligand coverage, young and the separation of water increase. So to take a look at the elasticity of the film in connection with this critical value. Well, we have showed that percent here seems to be critical value. But the other measurement, the nanoparticle become more viscoelastic and the interaction become weaker. So this figure between the theta and ligand concentration, which is 30% actually to 94% of the surface coverage. So we conclude that this beyond the critical value, there are just going to be a lot of thiols in the solution, and they run between the nanoparticles and are caught under the layers. Therefore, the film just loses the elasticity. So, summary, both MD simulations and X-ray scatter show that in the presence of the free thiols on the gold core or interdigitate, producing asymmetric shells. And in addition,
Binhua,
Shows a
you're
critical
really
value.
breaking up. It's a shame we can't hear your summary. Maybe if you just take a minute and go back into Gather Town and re-enter, maybe you'd have a better connection. Because I mean, it's such a lovely talk. I'm sure everybody would like to get to catch your summary clearly. So if you
So I stopped sharing and I go.
if you just go into Gather Town and then come back in, and then you can summarize, I think, because at the moment we can't hear you. Maybe yeah, try again now, but yeah, okay. So so we just wait. It just will take a minute for Binhua to go back into Gather Town and then press the button X to come back into the Zoom connection. Seems to be the day for connection problems. So I'm still, you can see there's two of me here. I'm logged in on my phone because my computer actually crashed a second time during this session. So now, okay.
Binhua's back, Bridget.
Yeah, Binhua, yeah, okay.
Yeah.
So
Okay, let me try
that's much
again.
better. We can hear you now. Yeah, great. So if you just want to do the summary again, then it would be really very kind. Thank you.
Okay, sorry about that. So in summary, the MD simulations and X-ray scattering shows that in the presence of free thiols, the bonded thiols and the free thiols interdigitate is producing a symmetric ligand. And in addition, the X-ray scattering, I'm not quite sure if the last slides show, and that's my important point, is the X-ray scattering shows there is a critical value of about 95%, above which the gold core separations become very large, and the gold nanoparticles moving away from the surface water. And so at that point, that could explain why the gold films lose the elasticity. So we conclude that the free thiols regulate the organization of bonded thiols and change the interactions of the nanoparticles with their surroundings. So if I have another 3 minutes, I'll talk quickly about our liquid interface instrument. We're funded by NSF. We're not part of APS. We're at sector 15, and the liquid interface stations share with two other techniques, crystallography and ASACs, and we run about 42% of the beam time. The instrument here was operational in 2002, and it's a single steering crystal geometry, which Ben described very nicely. We run experiments basically at about 66 to 60 keV. We have a very large sample table, which can accommodate bulky and large sample environment. And we have quite a lot of detectors here for different kind of experiments. Because of the strong demand from our user community for more beam time and new techniques, we recently funded to build a candle undulator at our beamline. So here we show the beamline optics. So the straight line, which is existing beamline, will get new monochromator and the mirrors. This monochromator, I want to point out, is a double silicon crystal and the multilayer crystals. And so the multilayers will enhance the intensity at 20 and 30 keVs. That was extremely helpful for the barrier interface experiment. And the Cybon's energies between 3.5 to 30 keVs, with this second beamline, it would double our capacity for everybody, and for liquid interface. Also, the straight lines still have a 40% beam time, but at the Kent undulator we'll have a 50% beam time for liquid interface experiments, and we're going to order this double deflector diffractometer, which Bridget and Tom pioneered. And we also can provide new opportunities for the community after the upgrades. I'm not going to read through all the areas for the interest in time, but I'd like to point out that this coherent imaging is one of our on the list. So this is our team pictures with PI and co-PIs here and the beamline scientists. We can see very happy. This is right after we heard that we'll be funded. And with that, I would like to thank for your attention.
Thank you very much for telling us all about the science, and congrats.